Before today's video, I'd like to give you an update. Today, I'm off for Europe. I'll be joining the Horner Europe team for Nuremberg SPS, what I consider the largest PLC show in the world. During the trip, 5 cities in 21 days, I'll be sharing short video logs so you can follow along. And Tuesday, December 2nd, during our normal time slot, I'll give you a full SPS show recap. I'm looking forward to the experience and bringing you along for the journey. Now, today's video. Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us for another Tuesday live stream. Well, one of the things I love about this channel is I get to work with a lot of equipment, and today is one of those days. Using Nidec control techniques VFDs with Horner. Now, I'm familiar with control techniques, but I've never done a deep dive on the Modbus connectivity, but that will change today. So if you're looking to interface a control techniques drive with a PLC in general, or a Horner PLC in particular, then today's topic should be right up your alley. Let's get started. Today we're going to start with some highlights from CT drives. We'll talk connection options and wiring with Modbus specifically. We'll talk different drive parameter settings. We'll go through Modbus register mapping, and there'll be plenty of demonstrations throughout. Here we go. All right, now Control Techniques offers several different series of drives, and one thing I like is there's a lot of consistency from drive to drive when it comes to parameter settings and those sorts of things. Now here's a few highlights we'll go ahead and hit today. So one thing I want to mention, and this was suggested to me by my colleague Jim Hausch, and that is he wanted to make sure I at least mention the fact that they have some really nice free software that you can use for online monitoring and configuration of your drives. But he also mentioned that even if you're not going to use their software for that, it's great as a real-time documentation tool. It's really the easiest way to look up all the details on drive parameters and drive operation. Everything's right there at your fingertips. And I will agree with Jim. I used it that way and it worked really well. Now, in terms of how drive parameters are organized within the CT drives, they're basically organized into menus, which is pretty common. And the way that they're notated is you have a 2-digit menu number and a 3-digit parameter number that's kind of, glommed together with a decimal point in between to kind of differentiate specific drive parameters in the drive. Another thing I really like is that there's a mathematical relationship between the parameter numbers, the menu and parameter numbers, and the Modbus register numbers, which actually allows you in some cases to calculate the Modbus register address just by looking at the menu and parameter number and doing it in your head. It's really very nice. Now, all the data available over Modbus is in integer format. So what you won't find is any 32-bit floating point encoded type values, which means all the values of all the Modbus registers are accessible in integer form. So if there are any implied decimal points, in tenths or hundredths, etc., those are documented in the parameter listings. Okay, now in terms of connectivity utilizing Modbus, of course they support Modbus TCP, which is certainly supported on the Horner product line as well as a lot of other PLC manufacturers. If you do want to utilize Modbus TCP, you will need an Ethernet option module for your drive, but they are available depending on the drive series you're using. Although I believe the high-end drives do come with Ethernet built in. Okay, also available from a Modbus perspective is Modbus RTU. So that's RS-485 based Modbus. For that, you'll need an RS-485 adapter that you can plug onto your drive. And of course, RS-485 is built right in to the Horner controller. So that's another option, and it happens to be the option we're going to talk about today with all the details you could need to talk RS-485. However, for those of you who are preferring to use Modbus TCP over Ethernet, our entire content today is pretty much applicable to you. You can just kind of skip over the parts where we talk about specific serial port settings. Okay, That's one of the parts we're going to talk about next, our specific serial settings. All right, so when we're talking about RS-45, we're talking about twisted pairs wiring. So you'll need one twisted pair to handle the actual communication signals, and then at least half of another twisted pair or an extra conductor that's used as a common. Now, why do you need that extra conductor as a common? Well, that's because of something called common mode. RS-45 supports some distances that are large, and you can have scenarios where the voltage reference for the communications is beyond the common mode limits of the equipment. So by having that common conductor, you eliminate that problem altogether. Now, another thing with RS-45 is that you have termination to deal with on the physical ends of the network. So if you have a CT drive at the physical end of your RS-45 network, you'll need to add termination, and you can do that by adding a jumper between pins 2 and 4 on the CT side. That puts a 120 ohm resistor in the circuit. Now on the Horner end, if the Horner happens to be on the far end or one of the far ends of the network, then you can simply turn on system bit SR152.3, and you can do that in your program or from the system menu, and that will enable 120 ohm termination on the Horner side. Okay, so make sure you handle termination. Now, another thing I want to mention about the twisted pairs wiring is that you don't necessarily have to use shielded twisted pairs. Okay, I'm showing a diagram here with unshielded wiring, and in a lot of cases that works just fine. However, if you are going to use shielding, you must handle the grounding of the shield properly, because if you don't ground your shield, it just acts as a giant antenna, adding the potential for noise and other disruptions to your communication signals. So if you do have shielded wiring, make sure you ground it. And usually it's best to earth ground it away from the drive, because the drive generates a lot of electrical noise. And by grounding it away from the drive physically, usually you'll have a better result. But make sure you ground it. That's the most important thing. Now let's talk about some of the parameters that we have to change to allow the serial communications to occur. Okay, now my philosophy in general, when you're talking about connecting a PLC to a drive, is usually I want to let the PLC adapt to the default serial parameters of the drive instead of changing all the parameters in the drive to match what I use on the PLC side of things. So in this example today, we're going to leave the default parameters for the serial port pretty much alone. And those default parameters are 19200 baud, 8 data bits, no parity, and 2 stop bits, and a Modbus address of 1. Now, of course, if you have multiple drives connected to a single PLC, they're each going to have a unique Modbus address. So at the very least, you'd have to change the Modbus address parameter on the individual drive so they have a unique address. And if any of those parameters are changed, and the parameter numbers are shown in yellow on the screen, if any of those parameter numbers are changed from a serial standpoint, you will have to perform a serial reset or a communications reset, which is menu 11, parameter 20. You'll have to set that to a 1, and then it will reset the communications parameters to what you've selected if you've made any changes from the default, and then it'll automatically set that parameter back to 0 after it's done with the reset. So that's a step you'll have to take if any of those change. Now, something I did in my example is I changed the start-stop method of the drive from its default, which is kind of a European style of control, over to a 3-wire start-stop control. Okay, and I did that through menu 6, parameter 4 by changing it from its default value to a new value of 4. Now, another thing you'll want to check is the frequency reference. Now, the default frequency reference, I believe, is voltage on one of the analog inputs. And if that's okay with you, you can leave it alone, which I did. Keep in mind, you can, by sending another parameter over Modbus, you can change the frequency reference for any given point of time to be supplied by the Modbus master, if you will. And that's what I did. So I left the frequency reference alone. And when I wanted to control the frequency from the PLC, I simply changed a parameter on the PLC side over Modbus, and then I was able to change frequency from the PLC. Okay. Finally, you're going to have to make sure that you've properly handled the hardware enable on the drive physically through a switch or some other, wiring there. And then you can verify you have got a properly enabled drive by checking the status in menu 6, parameter 29. So that's what I did kind of as preliminary setup for the demonstration today. All right, now let's talk about mapping drive parameters, your menu number and your parameter number, to Modbus registers. I mentioned the fact that there's a mathematical relationship that you can use, and that I really like that, and that's absolutely true. So let's go through that. So first of all, just to review what I said earlier, that is that all the data available in the drive is in integer form. Okay, so it's all available in holding registers, which are the Modbus addresses that traditionally have been numbered at starting at 40,001. It's all in holding registers, all right? And none of it is encoded in any kind of floating point format. So any decimal points are just implied and they're documented, and you'll just have to do simple divide by 10 or divide by 100, that sort of thing in your logic. All right, now to make that conversion from menu number, parameter number over to Modbus address, let's start with Modbus 5-digit addressing. So to do that, you take the menu number for the parameter you're working with, multiply that by 100, and then add in the parameter number. So for example, if I'm looking at menu 7 parameter 1, then to calculate the Modbus address, I just take menu 7, multiply by 100, that gives me 700, add the parameter number to it, that gives me 701, and then add that final number to 40,000, and I come up with a Modbus 5-digit address of 40,701. Okay? Really straightforward. Now that's the official way to do it for 1-bit, 8-bit, and 16-bit data. Officially, if you've got a 32-bit parameter, all right, you have to take an extra step and add an additional 16,384 to the address number. And in this example of menu 7 parameter 1, you would end up for a 32-bit value of 56,505. That would be the Modbus address you would be using. Now, strictly speaking, Modbus addresses greater than 49,999 are illegal, which means that you wouldn't be able to access those using purely 5-digit addressing. So that would kind of imply that we're going to have to use another method of doing it. Well, first of all, I'll show you later why 5-digit addressing actually does work a majority of the time. But for now, let's talk about the alternative of 5-digit addressing, which is 6-digit addressing. With Modbus 6-digit addressing, which the drive also supports and the Horner also supports, the starting holding register number is 400,000, not 40,000. So you use the same exact formula as before, but you add your calculation to 400,000, and you end up with our example of menu 7 parameter 1 of a Modbus 6-digit address of 400,701 for the case of 1, 8, or 16-bit data, and 416,505. Remember, we had to add 16,384 to the end step there for 32-bit data. Okay, so again, you're thinking, well, I'm sure there's probably some drive information I need that's 32-bit type data, so I'm probably going to have to use 6-digit addressing. Well, again, not so fast. There are some things we can do where 5-digit addressing will work just fine in a lot of applications. We'll cover that here shortly. Okay, so for the demo we're going to be doing today, and again, the particular parameters that you need to access are going to vary by, very greatly by application, but there's a couple that you're going to find are going to be very common for most applications, starting with the status word parameter. Okay, the status word parameter is a bit-mapped group of bits that are all mapped to a word, and those are ones that we monitor from the PLC to check the status of the drive at any given point in time. So that's one almost everybody's going to be using. And then there's also on the other side, the control side, there's also a control word, which I've also got highlighted there, which is a bit-mapped group of bits that we can turn on and off individually to control the drive the way we want. And then in addition to that data for today's demonstration, I've also got some data I'm going to be monitoring on a read-only basis. What's the frequency of the drive, the voltage, the power, the RPM. Those are just examples showing you how to monitor that sort of data with read-only information. And then on the output side of things, in addition to my control word, I've got a bit that I've got to turn on to enable the control word. And then I'm going to be controlling the frequency of the motor, of the drive effectively through an additional read-write parameter. So that's what we're going to be working with during today's demo. Okay, the details of the status word are shown here. They're also documented in our example program you'll see today, so I'm not going to spend much time on this particular slide. And then the details of the control word, also, these are bits we can turn on and off to control the drive. Again, all well documented in the application program example that you can download, and then on this screen if you want to freeze frame it. Okay, now let's talk about mapping these parameters that I talked about using for today's demo over to Modbus addresses. All right, now you'll notice in my list by looking at the type column there in the middle that there is a mixture of 16-bit data and 32-bit data we're going to be accessing. So you would be thinking, well, we definitely are going to need to use 6-digit addressing to be able to access all 32 bits for all those parameters. Well, one thing that you may not realize, and I think CT does a good job of this, is if you've got a parameter which is 32 bits in size, you can still access the lower 16 bits of that parameter without any problem. Okay, well, why would you want to do that? Well, let's take a look at that last column. I've highlighted the parameters that are 32-bit parameters, and the largest value that you would get from those parameters if you just looked at the lower 16 bits. And when you do that, you'll see that, are we ever going to exceed 327 hertz? Probably not. Are we ever going to exceed 327 kilowatts? No. How about 32,000 RPM? No. How about 327 hertz in terms of controlling the frequency? No as well. So as you can see that for the parameters I've selected at least, and for a lot of other parameters, even just accessing the lower 16 bits of a 32-bit parameter will work just fine, because you'll never need to set the value higher or high enough to get into that second word. Okay, so in my example, we're going to do two different demos today. We're going to do a demo using 5-digit addressing, where we just access the lower 16 bits of 32-bit parameters. And we're going to do an example using 6-digit addressing. And as part of that demo, we're going to actually access all 32 bits of 32-bit parameters. Okay, so that's what we're going to do in our demonstrations today to demonstrate that you do truly have a choice in terms of which approach you want to take with 32-bit data. Okay, so here is our 5-digit Modbus data map, and you'll notice in that 5-digit column there that all those values were easily calculated based on the parameter number. So let's take a look at that first one. So with status word, the bitmap status word, it's accessible from menu 10, parameter 40. So if we do the math, we take 10, multiply by 100, that's the menu number, that gives us 1,000. We add the parameter number to it, that gives us 1,040. And then we take our 1,040 and add it to 40,000, and we get our 5-digit address of 41,040. So we do that same process with each of those other parameters on the list there, and that's what we end up with for our 5-digit Modbus data map for our first demonstration. All right, so let's dive into that first demonstration, show you how to set up on the Horner side, and then we'll show communications happening on the bench. Before we dive into things on the Cscape side, I did want to at least briefly show you the excellent free software from CT Connect. And I'm not even using it online. As you can see here, I'm offline right now. Of course, it has capability for configuring the drive, monitoring drive parameters, all those sorts of things. But I'm just using it as a real-time kind of reference book, if you will, an online reference book, and it's outstanding for that. So right now, I've pulled up, menu 10, parameter 40, and it's giving me all the details on, that's the status word in this case, giving me all the details with real-time links. If I wanted to take a look at the details for motor RPM, which is in menu 5, I could find that here, and it gives me all the information on that one. It shows the minimum and the maximum and those sorts of things. Is it 32-bit or 16-bit? All that kind of good information. So even if you only use it as a documentation resource, as I have, this is really excellent software. Now let's take a look at the programming we need to do in Cscape to set up communications and control the CT drive from a Horner OCS. All right, now let's start with the Modbus setup on the Horner side. So to do that, we're going to go to the hardware config, and we're going to go to serial ports. Now, if we had Modbus TCP, we would go to LAN 1 and configure Modbus TCP from there. But we're doing Modbus RTU, so we click Config under Serial Ports. Here you'll see under MJ2, which is the RS-45 pins on the MJ1/2 physical port, we've selected Modbus Master. And we've got 3 levels of configuration to do. Let's take a look at that. So on the highest level, remember this is serial communications, we're going to match the baud, parity, and stop bits to the defaults of the CT drive. Now we don't have to do it that way, but that means less drive parameters to change. So we're matching the Horner to match the drive defaults. We've selected Modbus RTU protocol. And then the other things that we've changed, we've reduced the timeout down to ½ a second, which is plenty fast enough for a point-to-point network. All right, so that's how long the OCS is willing to wait, or the Horner is willing to wait for the drive to respond to any queries. If we ever have any timeouts, we'll do some retries. That's the same as the default of 2. If we ever have to, reacquire the drive, maybe it's been powered down for a while and it's not responding, we've lowered our reacquire time way down to ½ a second as well. Again, for a point-to-point network, you don't need long timeouts. And then we have taken advantage of the status information that's available for the master. So this is 4 consecutive double words that tells us how communications is going. I'll show you a slide later that details what each of these status words means. All right, so that's the top level of configuration. On the device level, this is where we tell the master about the slaves it's going to be connecting to or communicating with. All right, we've given the slave device a convenient name. I've just called it CT-M400 because we have a UNIDRIVE 400. Also, we're going to use 5-digit addressing for this first demonstration. We'll use 6-digit on the next demonstration. All right. We've also taken advantage of the status that's available from the slave. All right. So again, we want all the status we can get in case we have trouble and we want to be able to debug with the most information possible. And then finally, in addition to selecting 5-digit addressing for this particular demonstration, we also have checked swap 32 words on 32-bit data. Now, if you're not accessing any 32-bit data, you don't necessarily need to do this, but CT, when 32-bit data is returned, they send the data back in the order opposite of what we would expect. So that's why it needs to be checked if you're going to be accessing any 32-bit data. All right, so that's the slave level of configuration where we tell the master about the slave. And then finally, we have our scan list. Now, this is the list of all the Modbus data we're going to be reading and or writing, the addresses for the data we're going to be reading and or writing, and where it's going to be stored locally in terms of local variables. So let's quickly go through all the entries in our scan list here. If we were adding them from scratch, we'd hit the add button, but since they're already here, I'll just double click. Okay, so this first parameter is our status word, and we're going to read it from 41040. That's the 5-digit address we calculated based on the menu and the parameter number. It's just one word of data, and we're going to store it in a local variable called CT_status, and it's to pulled read. Okay, so that's our first entry. The next entry is 4 consecutive words that we're going to be reading in, starting at 4501, that's the Modbus address, and we're going to copy it into this local word array. Now, intermingled with these parameter numbers, you're going to find there's some 32-bit parameters in here. But remember, we're just going to be reading the lower 16 bits of those parameters and storing the lower 16 bits of those parameters in the variable array I've detailed here, okay? So because of the fact that the data values that those parameters will have are going to fit easily within 16 bits, this is going to work fine, okay? So anyway, so we've copied these 4 consecutive words into this array. Later on, we'll split them out into individual variables in our program. And this is just, again, a pulled read. All right, we have then 2 final parameters that are part of our scan list that are both read-write. We have our control word. Actually, we've got 3 parameters, but 2 different entries in the scan list. The first 2 that we're going to read-write are the control word and the control word enable parameters. Okay, so that's 4642 and 4643. Okay, we're going to read write those two consecutively. That's more efficient than two separate entries in our scan list. They're going to be written from this particular word-based variable array. The first word is our control word bits. The second word is our control word enable bit. All right. And again, this is a polled read write. And then the final entry in our scan list is our frequency reference. In other words, if the PLC, or the OCS in this case, is telling the drive how fast to run the motor, then we're going to need a frequency reference variable. So this is the local variable in the OCS, and that's where it's being written to in the drive. Okay, so that's our scan list from a Modbus standpoint and the complete Modbus configuration. Now, what else is involved in our program, in our example? Well, I'm not going to go through it in a lot of detail. You can look through it very carefully if you download this, but I will say that from the status words, we're mapping some of the status words that we get from the drive that we're getting in over Modbus. We're mapping them to specific inputs in the program. We also have control words that we're mapping from specific variables here. Okay, we're generating a Modbus OK bit based on the status feedback we're getting from the Modbus status information. So there's just a little bit of logic in here for that. Now, from the standpoint of screens, let's take a look at the screens that we've developed. First of all, we've got a start-stop screen, if you will, where we can start and stop the drive, we can enable it, put it in auto or manual mode, we can make forward or reverse direction decisions here. We can decide whether we want the frequency reference to be from locally on the drive itself or from this value here. We have some, parameters we're monitoring over Modbus that we copied into actual variables we are displaying here. So lots of good information here on this first screen. And then I've also created a second screen, which gives us a lot of good status for the drive. What is the full value of the status word? What is the full value of the control word? What are the individual bits mean for the status word? What are the individual bit statuses for the drive control word? And then again, our diagnostics over Modbus to make sure everything's happening okay. So this is the Cscape configuration, again, specifically for the 5-digit addressing example that we're doing here. Next, we're going to go on the bench and take a look at how things run. Okay, let's take a look at how things are on the bench here. So here's that main control screen that I showed you in Cscape. But before we dive into that, let's go to that second screen and take a look at what's happening here. So here's our Modbus status, real-time status, and you can see our good responses are counting up. We've got good messages happening, which helps us generate this Modbus OK status internally in our logic. If we take a look at the individual bits from drive status, we can see where the drive stands right now and which bits we've set from a control standpoint in the control word. Okay, but if we're going to make this thing move, we're probably going to need to enable the drive, probably going to need to put it in automatic mode, those sorts of things. So let's go back to the first screen, okay, and I'm going to go ahead and click enable. Let's go look and see if that had the desired effect. Yes, drive enable is on. Okay, let's go back. Now set automatic mode on again, looking at our status information. Yep, the auto bit is now on. All right. Now, in terms of actually controlling frequency, we've got a couple different ways we can do this. Right now, I haven't selected for the frequency reference to come from the PLC over Modbus. So let's leave that off for now. And then we should be able to control frequency from the analog input going into the drive itself. So let's go ahead and try that out. Let me start the motor. Okay, and now I can adjust the analog voltage going into the drive to control the frequency. Okay, so you can see my commanded frequency hasn't changed, but the frequency of my drive is considerably higher than that based on the fact I'm turning a pot that's connected to that analog voltage input. Okay, so let's go ahead and stop that now. Okay, and now I'm going to switch to having the frequency reference come from the OCS, okay? And so I've made that selection. Now when I start it, we should just go up to 30 hertz. So let me go ahead and start that. Okay, and sure enough, we did go to 30 hertz. Now, it's not exactly 30 hertz. This is interesting. So if you know the answer, you can, if I've got the wrong answer, you can put this in the comment section. But here we're seeing 31.16, even though we're commanding exactly 30 hertz. Okay, and you can see on the keypad of the drive, or the display of the drive, that it's receiving a command of 30 hertz. But possibly, if we take a look at the documentation for this parameter we're monitoring for current speed, it says it's the sum of final demand reference and the motor slip compensation frequency. Maybe the motor slip compensation frequency is what's causing that little bit of a offset there. Don't know for sure. But anyway, if you know, put it in the comment section. All right, and then I can go ahead and stop this guy here. So as you can see, everything's working great. Oh, one other thing I want to mention. Let me go ahead and start it back up again. So we're getting what look like legitimate values over here, even though we're only reading the lower 16 bits of those 32-bit parameters in the case of RPM and kilowatts. So I think this is working just as we would expect, even though for those particular 32-bit parameters, we're only reading the lower 16 bits. Now, before we move on to our second demonstration where we go through 6-digit addressing and accessing all 32 bits of the parameters, I want to remind you, if you're using Horner controllers with Modbus, where the Horner is the master or the client, always take advantage of the status information that's available to you. It'll tell you if everything's working properly, and if it's not, it'll flag that as well and give you some error codes that you can use to debug what's going on. So that's just a reminder, use the status that's available to you. Okay, now as we move on to our 6-digit Modbus TCP demo, I want to show you the parameter numbers for 6-digit Modbus. So first of all, for the basic 16-bit parameters, okay, the calculation is the same as before, except we add our, menu times 100 plus parameter number sum. We add that to 400,000 instead of 40,000. Now, for those that are highlighted in red, those are 32-bit parameters. For those, we have the extra step of adding 16,384 to those values, okay, in addition to the earlier calculation, to come up with what you see there in red. So this is effectively the 6-digit Modbus addresses we're going to use for our next part of our demonstration. Okay, for the 6-digit Modbus addressing demonstration, I'm only going to show you really what's changed. So let's go back into the Modbus configuration under Hardware Config, under Serial Ports, because we're talking Modbus RTU. Nothing has changed on the network side of things. On the device configuration for our CT drive, this time we've selected Modicon 6-digit addressing. And again, it's critical that this checkbox be checked so that the 32-bit data that we retrieve comes back in the proper order as far as the OCS is concerned. Okay, so that's what's changed here. And then on our scan list, what you're going to see is you're going to see much larger Modbus addresses, of course, because 6-digit addresses for holding registers, those start at 400,000. Also, you'll notice that we're reading double words in the case of that status information, not the status bits necessarily, but the voltage and the RPM and those type parameters that we're monitoring. We're monitoring those using the 6-digit address, and again, we're accessing all 32 bits, so we have to add 16,384 to the address before we pop in that number, which we've done here, and we're reading 4 consecutive 32-bit addresses here, okay? Copying those into an array, and then we're divvying out those specific variables in our ladder logic, okay? So that's the difference you see here, is that larger address, 6-digit addresses, and for the ones where we're accessing 32-bit data, we check this 32-bit access button. We have larger addresses, obviously, address numbers, and then that's the main differences that we're seeing here. Okay, so that's really the big difference between the 5-digit and the 6-digit addressing approach, and that is the addresses as well as how much data we're reading back at a time from the variables that are 32-bit in length. Okay, so that wraps it up. Let's take a look at the bench and just verify that it operates the same. Okay, I've just downloaded my program with the 6-digit Modbus addressing. Let's just verify everything works the same. So I'll go ahead and turn on the enable, turn on the auto. We'll go with the local frequency reference here, which is currently at 36 Hertz. And I'll go ahead and start the motor, and everything basically works the same as before, as it did when we were doing 5-digit addressing mode. And because of the fact that none of the parameters are really going beyond values that can be handled in a single word, that I'm not seeing anything different by reading all 32 bits in the parameters than I would be if I was reading just the lower 16. But anyway, everything works fine in my example in both cases. If you'd like more information on Control Techniques drives, by all means contact your local Control Techniques distributor. Now, if you happen to be in Minnesota, North Dakota, South Dakota, Wisconsin, Nebraska, Iowa, Illinois, then the Powermation team is definitely a CT distributor and a Horner distributor. And they are the ones that help provide me with the equipment I needed for this demonstration today, and my friends Andy, who loaned the equipment, and Jim Hausch, who gave me some good pointers to make sure I, covered the salient points with all of you. Special thanks to those two guys. All right, now, if you're interested in OCS training, we've got a couple of courses scheduled for the first quarter. Get to our website and get signed up today. The biggest trade show in the world, as far as I'm concerned, is SPS Nuremberg. And the Horner Europe team will be there, and I'm going to be joining them. So I'll have my camera and my microphone. I'll be, recording lots of footage and talking to the Horner Europe team. I'm looking forward to doing that video and looking forward especially to being in Europe. So if you can get there, by all means do so, because as I mentioned, SPS Nuremberg, as far as I'm concerned, is the biggest PLC trade show in the world. Also, if you'd like to interact with Horner online, you can do so on our website at hornerautomation.com, on our YouTube channel, or on LinkedIn. Now, next week, while I'm in Nuremberg, we are going to be showing in our normal Tuesday time slot a video that I pre-recorded on data logging. This was by customer request, and we're going to cover data logging in plenty of detail. So if you'd like to have, complete understanding and potentially complete control over the data logging that may be happening on your Horner controller, join us next week. If you haven't subscribed to our channel yet, don't hesitate to do so. It doesn't cost anything. And if you choose notifications when you subscribe, you'll be notified every time we go live or every time we post a new video. Okay, so until next week, when we talk data logging, let's all get out there and do some good.